Hi, thank you for attending. My name is Rafael Mayo, and I'm going to present this work about virtualization framework for remote GPU utilization. We are working in this project at the university, the Technical University of Valencia and the Universitat Jaume I of Castellón in Spain. And we have been working for about 2 years in this project, and now we think that it's ready to use in production systems. I am going to make a small introduction about GPU computing, because it's important to know which is the focus of our work. Then I introduce our framework, the remote CUDA framework. I compare this remote CUDA framework with other GPU virtualization frameworks that exist. And at the end, I will present the integration of our tool with one job scheduler, the SLURM job scheduler. And at the end, I will present some real applications test and performance tests we have done. Okay, GPU computing, as all you know, defines all the technological issues for using GPU's computational power for executing general purpose code. It has made a remarkable growth in the last year. In fact, in the last top 500 list in November, it appears more than 10% of the supercomputers using some type of accelerators, and it has been in the last year when this accelerator has been integrated into these supercomputers. The basic building block of a GPU computing system is a compute node with one or more GPUs. It can be inside the box of the GPU, or it can be outside of the box of the GPUs, but in both cases, all are connected using the PCI Express bus. From the programming point of view, a programmer can see a GPU computing system as a cluster, a set of nodes, each of one with one or more GPUs, with one or more GPUs, and with the characteristic of a disjoint memory spaces between all the GPUs and the CPUs. And of course, we need an interconnection network in order to perform collaborative work. The use of the GPU computers has grown thanks to the development of tools that has eased the programming of the GPUs. The two main approaches that exist actually are the CUDA, that is NVIDIA proprietary, and OpenCL, that is an open standard. But basically, both approaches have the same working scheme. There is in the compilation step, you generate GPU code and GPU code in separate kernels. We know the GPU code as GPU kernels, and on the execution time, because of the disjoint memory spaces between GPUs and CPUs, there must be data transfer between CPU and GPU memory spaces. Then, before executing a kernel, you need to transfer data from the CPU memory space to the GPU memory space. Then you can execute the kernel, and after the kernel execution, the results must be copied from the GPU memory space to the CPU memory space. Then these memory copies is an overhead for the operation, and here you can see the influence of data transfer for a simple test that is a matrix multiplication. When we have small operations to do in the GPU, this memory transfer has a height effect, a height overhead over the time, while when we have a lot of work to do in the GPU, this overhead is very low compared with the computation. Then not all the problems can be take profit of the GPU computational power. There must be data parallelism in the code. If we have not data parallelism, we cannot use the computational power of the GPUs, and we divide the use of GPU computing in 4 different scenarios. If you have low level of data parallelism, you are not a candidate for GPU computing. You must execute your code on the standard CPUs. If you have high level of data parallelism, you are a good candidate for GPU computing. And in this case, the best you can do is to put a GPU or a set of GPUs in each node and use it as time as possible. And there are 2 other scenarios where you have a moderate level of data parallelism. That is, you have only some applications that can be that can take profit of the GPU computing, or your application has only part of the code that can take profit of this GPU computing. Then, if you put a GPU in each node, more of the time, or a lot of time, these GPUs will be idle. And there is another scenario that is applications that can take profit of multi-GPU. That is, an application that can use the GPU computing power, but for more than 1, 2, or 5 GPUs that you can have attached to a node. Then our approach is good for these 2 last scenarios, when you have a moderate level of data parallelism and when you have applications for multi-GPU computing. Then I am going to introduce our approach for virtualization of the GPUs for GPU computing. What is remote CUDA? Remote CUDA is a framework for enable that a CUDA-based application running in one node can access GPUs on the other nodes. As I have said, we think this is useful when you have moderate level of data parallelism and applications for multi-GPU computing. What we have done is a framework in which, if you have a configuration like this, you have a small cluster or grid cluster, but you have put GPUs only in some nodes. With virtual GPUs, what you have is that each node has access to all the GPUs in the system. So each node in the cluster can see as many GPUs as you have in all the cluster and can use them for the computations. This is the typical CUDA application. You write the application using the CUDA libraries that are in charge of sending and executing the code in the GPU. What we have developed is a client-server infrastructure, such that we have a client side with the application, and we put the server side in the node who has GPU attached. Then we substitute the CUDA library for our own remote CUDA library. We put a remote CUDA daemon so that when an application has to use the GPUs, the information, the kernel, and the data that you are going to use is sending to the server. The server executes the code in the CUDA device, and when you finish the execution, you send back the results or the information about the execution to the client, which don't know that its code has been executed in other node. This is a basic way of running an CUDA application. You have an initialization step. You have to communicate with the server in order to initiate the GPU. You have to know which GPU you are going to use and where this GPU is connected. Then normally in a CUDA application you have to make a memory allocation on the remote GPU. there must be some data that must be copied from the CPU to the GPU memory spaces. In this case, from the client to the server. The server has the GPU and the client has not the GPU. Then kernel execution on the server side. Once the kernel has been executed, the results must be transferred to the client. There must be a GPU memory release in order to free the memory, and at the end there must be a close of the channel that has been used in order to communicate the client with the server. We have 6 basic modules in our framework. The interception library, we provide binary compatibility, so if you have a code that has been written for CUDA, you only have to run the code using our library and it can run. We have a interface with the communications, and we have two main communications modules. The TCP module, in order to test for functionality and for installation where you don't have high performance network, and an InfiniBand module in order to take profit of all the high performance InfiniBand network. The last part of the framework is the server daemon that is in charge of receiving all the petitions and executing the code in the CUDA device. Then we have put a lot of effort in the optimization of the communications. In order to optimize all the communications, we use GPU direct to avoid memory copies. We use a pipeline protocol in order to improve the performance, so we can use pre-allocated pined memory buffers, and we have to look for, evidently, for the optimal pipeline block size if we use a pipeline to make the communications. When you are using CUDA, there must be two types of memory allocation: pageable memory or pinned memory. And you can make synchronous transfers if you are using pageable memory, and you can make asynchronous transfer if you are using pinned memory. Then, in case you are using pageable memory, in the client side we have pre-allocated 2 buffers of pinned memory in order to improve the performance, and other two buffers in the server side. Then, when we want to send information, that is the kernel or data or whatever information you need to send to the GPU, there must be a first operation with a send rec operation in order to advise the server that a communication is going to be done, and at the moment, with a set of send rec operations, we send all the information from the client in pieces of the same size of the buffers we have pre-allocated in both sides of the client and the memory. So at the end, what we have is a three-stage pipe with pinned memory, so that we can increase the performance of the communication. So at the end, you can send all the information with a low overhead. I will show you some results with a low overhead over the overhead you have if you are sending this information to a GPU directly connected in your node. In case of the user has allocated pinned memory for the CUDA operation, you can use asynchronous transfer. In this case, we need a send rec operation over the InfiniBand in order to start to advise the server. But once we know that it's an asynchronous transfer with pined memory. This will be the main memory in the client, but it's pined memory in the client and it's pined memory in the server side. We send in parallel all the remote reads, and as they are completed, we have, in this case, a two-stage pipe in order to send information to the server. Then the first thing we have to establish is which is the beta site for the for these buffers. What is the beta site for the chunk of information you are going to send in each operation? We have tests with a FDR InfiniBand and a Tesla K20, and we have seen that this is the line for CUDA, for directly connected GPUs, and this is the line of the throughput for the best size of buffer, that is 1 megabyte, in order to obtain the beta performance of the network. So we established that 1 megabyte is for us the best buffer size in order to communicate from the local client to the remote GPU memory. This is the throughput we obtain with this 1 megabyte buffer with FDR and with CUDA InfiniBand and with a gigabit Ethernet. We are very close to the throughput of the CUDA for copying in local GPUs. This is with pined memory in a host to device copy, and this is the host to device with pageable memory. Here we have an unexpected result that we are better than the CUDA to the local GPU, and this is because we use pre-allocated buffers that help us to have better throughputs than a local copy to a GPU. This has been the good news. These are the bad news. Not all have to be good news. The bad news is for the latency. We have made a study of our framework for sending small packets, 64 bytes, and make a set of iterations, sending this information to the remote GPU, and we have seen that our latency is not as good, evidently, like as the latency of a local GPU copies. This is because for this small size of bytes, the copies in the client and the transfer over the network has a lot of impact against the only copy the information in a local GPU. Okay, there are other GPU virtualization frameworks. In fact, this is what we have found in our study. You can have here which version of CUDA they support. Our rCUDA support the CUDA 5.0, and there are other gVirtus, gSCUDA. vCUDA, gBeam, AgriCUDA are more focused to virtual machines, and vGPU is a commercial product. We have this is are put it in gray because we have not able to test them, but we have tested the rCUDA, gVirtus, and gSCUDA. About latency in the communication between local memory, local CPU memory, and remote GPU memory, we see that the best results are for gSCUDA, but gSCUDA doesn't support pined memory. And in all cases, the results evidently are better in CUDA that only copies memory in the local device than when you try to use whatever remote GPU in the system. In bandwidth, if we test the bandwidth for pageable memory, we can test the SCUDA in this case. We can see that our solution is the best one. This is the same result that I have shown previously. Instead, we are going faster than, going better than the local CUDA copies. In device to host using pageable memory, we are going to we obtain better results than rCUDA and Virtus. And the same happens with PineNet memory. With PineNet memory, we only can compare against the Virtus. We obtain good results, very approximately about the CUDA results, and the same when using the copies device to host using PineNet memory. Then, with this, with all the implementation done, the tool can be used, but we have to see how to integrate it with a job scheduler, how to schedule the GPUs between the possible jobs that can use it in a real cluster. So at the end, we have a make integration of rCUDA with the SLURM job management. SLURM is a job scheduler for Linux systems. This scheduler does not understand anything about virtualized GPUs. SLURM can manage GPUs with a general resource module that it has included in the latest versions of SLURM, but we have to add a new general resource for manage these virtualized GPUs. In that way, the place in which GPUs are in the system are completely transparent to the user, and the user, the only thing that has to do is to, in the script or in the summation command, specify the number of remote GPUs that needs for the job. This is the structure of the SLURM. As many job schedulers, has a controller daemon and a set of daemon in each node of the system, and a set of commands in order to send jobs or make requests to the controller daemon. Then we have introduced a new part of software to the SLURM job manager in order to know about remote GPUs. So the only thing we have to do is in the SLURM configuration file indicate that there is a new general resource that is a remote GPU, and in the nodes that has GPUs connected, identify which of these nodes has remote GPUs available for all the nodes of the system. Then, if we control the behavior of the SLURM, we can send a control command, and this control command says us that SLURM understands a new resource that is a remote GPU. In the configuration file for the nodes, we have to specify the remote GPUs we want to use in each node with GPUs. We have specified the memory of these remote GPUs because at the moment we can share one GPU between several jobs until all the memory of the GPUs is completed. Then, when we want to run a job, we only have to say to the SLURM job scheduler that we need for GPUs how many memory of the GPUs we need for our execution. there is a set of environment variables that will be used by the remote CUDA client in order to send the information required for the remote GPU execution. This is completely transparent to the user. Then, basically, what we have to do is here in this picture, you can see what will happen if you have 4 nodes. In node 0 you have two GPUs, and in node 1 you have only 1 GPU. If you try to run a job that needs 2 nodes and 3 GPUs, SLURM without remote CUDA says that it's unable to allocate resources because you have 3 GPUs, but SLURM needs the 3 GPUs in the same node. What we have to do is to decouple the GPUs from the nodes, so you can use whatever GPU in the system exists. So you can perfectly send a job that needs 2 nodes and 3 GPUs, having these 3 GPUs connected to whatever node in the system. Then for the end, I will present some real applications test and SDK. This is the test system for the first test. This is a system with 2 nodes, one without GPU and one with GPU. The one with GPU has a Tesla K20, and we are using FDR in order to communicate the two nodes. This is an execution of all the CUDA SDK examples. Here we not consider the examples with graphic calls because we have not implemented the graphic support of the CUDA. Here you can see that we have a relative big overhead over the execution on a local CUDA. This is because most of these examples has very little work to do, so the communications are in this case bad for the test. But here you can see an example of one of bioinformatics software. Don't ask me about this. I don't know what is this software. We just take the software, make install, and make test. And if it runs, it means that our software is good because without knowing something about this application, we can run in a remote GPU. Here you can see that the lines of CUDA, the blue one, and rCUDA in FDR and QDR are almost showing the same time for the execution. The bars indicated the overhead of the FDR and QDR and gigabit Ethernet. InfiniBand overhead is almost negligible in this execution. There is another application, Q++. In this case, we see that we perform almost at the same level as the CUDA, executing in a local GPU, and we are using a remote GPU. And for the end, I want to show you some tests for multi-GPU. That is, try to use small GPUs that the GPUs you are directly connected. In this case, for CUDA, we use one node with a Tesla with 4 Tesla's GPUs. Tesla is 2050. And for rCUDA, for remote CUDA, we use 8 nodes, but the test is running in one node, and what we do is use all the GPUs of the different nodes. Then this is the test for multi-Carlo multi-GPU that appears in the examples of the NVIDIA SDK. As you can see, the dark lines, the dark bars, are for CUDA. We can only arrive to use 4 GPUs because only have 4 GPUs attached to our node. But with our CUDA, we can use the 8 GPUs in the system. This is the trend line of the rCUDA, and we can see that this is one application that can take profit of using more GPUs than the GPUs you have directly connected to your system. Another time, the bad news is that not all the applications can take profit of this. This is an example of the execution in which putting more GPUs to work in a program don't take benefit of it. This is an example where we use a matrix multiplication from the LeafFlame, a library for high-performance linear algebra. And in this case, putting more GPUs to work for this operation is not a good idea because we can obtain better results. What are done now in rCUDA is to improve the scheduling that we have introduced to SLURM. Now we only take into account the memory used for each job. We have made tests in using ARM platforms. In this case, we use KarmaBoas as a client, and we put the remote CUDA daemon in an Intel platform with a big GPU, a Tesla Fermi GPU. We have tested with this KarmaBoas all the NVIDIA SDK examples, and the functionality is okay, and we have tested also the LAMPS molecular simulator, and the results are okay. But I have no present performance. We have only the first numbers, but we expect limited performance because in Karma we only have a 1 gigabit per second Ethernet. If we can have an R platform with a better communication network, we can have as good results as I have presented. We are going to test the rCUDA with most of the popular GPU accelerator applications from NVIDIA, and now we are studying the support for CUDA 5.5 that has been the last release candidate from NVIDIA. And that's all. Thank you.